Just going to get up to 20 minutes, including questions. So if we run out of time and you had questions, please talk to the authors afterwards. Please refrain from taking any pictures, any video. This is a copyright belongs to the speakers. We'd like them to come back next year and want to present and not be concerned about their intellectual property being used somewhere else. So our first speaker this afternoon is Brenton Fletcher. He is a research fellow at UQ, focusing on applications of biopolymers. The title of his talk today is Modifying Wheat Starch for the Selective Depression of Hydrophobic Gangue.
Thank you, Renelle. Thank you all for turning up, learn about some starch. I'd first like to just thank my student, Wanda Chimonyo, who's done most of the experimental work that's included in this presentation today, and also Professor Yongzhun Peng, who oversees the work and the project. As quickly, I'm talking about carbon as the hydrophobic gangue today, and in the case of copper flotation. So I imagine many of you will be aware that carbon is a common problem in base metal sulfide flotation, and particularly in copper. Historically, inorganic reagents have been used that will depress the carbon, and the advantage of potential natural polymers like starch or CMC or guar gum offer the potential for non-toxic, renewable, and biodegradable alternatives to the inorganic toxic depressants. Why do I want to focus on starch? Well, I have worked a lot of starch more from a polymer science and polymer engineering background, and I've decided the last couple of years to have a bit of a foray into minerals processing and see how it works there. Starch is readily available, has many sources. It's the energy storage of the plant kingdom, and as such it is inexpensive and it's environmentally benign. In general, the polysaccharides like the guar gum and the carboxymethylcellulose and that, the depressant mechanism is essentially that once it's absorbed to the mineral surface, the excessive number of hydroxyl groups that exist along the polymer chains will form the hydrogen bonds with the water phase and render it hydrophilic and cause it to sink. If you're going to use starch in flotation, you have to overcome its granular structure, and that's what we call doing a gelatinization, and it's usually achieved by mixing the granules in a aqueous environment and with caustic usually, or with heat. But if you're going to do this on site, it's got a couple of issues there. You're going to have to have infrastructure like the tanks, the preconditioning tanks for the pre-treatment. You're going to have to handle the caustic, and that can be in some environmentally sensitive areas. And in general, native starch as it stands doesn't have the best selectivity. So that's one of the things that we were trying to develop and advance in my work. So the goal, I suppose, is to create modified starches, tailor their physical and chemical characteristics, and look to improve their selectivity. Ideally, they want to be cold water soluble to overcome that need for the gelatinization. There's a bit of a background on the chemical structure of starch. It's made up of alpha D glucose units. You can see up in the top left there. All right, on the top right there. You're right, my right, your left. And it's made up of two polymer types, I suppose. The amylose is generally a linear polymer with molecular weight, say, up to about 1 million. Does actually have some long branches, very rarely along the chain, but it's generally regarded as linear. And mylopectin or amylopectin, depending on where you come from. And it's a very large polymer. It has the branches, and it can have well above 1 million and tens of millions, and even above that in some cases. I'm talking about wheat starch. I'm talking about wheat starch because that's what we grow in Australia, is a lot of wheat. And the company I work to do this project with, or supported some of this work, is Australia's largest processor of wheat. It's peculiar in the fact that it has a bimodal distribution of granule sizes, so just referred to as A size, a large size, and B size, a small size. But if we're going to use this in the flotation, we need to unlock those granules. You can see here that there's quite a complex structure. These molecules I just showed you on the page before are organised into this helical structure, and within that there is the amorphous and the crystalline regions. And so after all this, like I say there, it works well as a biological battery, but if you want to get the molecular potential of starch, you have to unravel these things. The research approach was, number one, try to improve the solubility, especially cold water solubility at that. And looking at the concept of flotation, all you're doing is playing with the hydrophobic versus hydrophilic. So the simplest thing is to do is look along your functional group change. There's a rule of thumb there. We can move from, well, starch has the hydroxyls in its native structure. If we can produce carboxyls, it'll be more polar. And if we go down the other way, we'll get more hydrophobic type of character to the starch. So what process is going to achieve this is essentially oxidizing. Is a simple way to start. So what we did is you can look at oxidizing starch to introduce carbonyl and then carboxyl functional groups. It'll introduce scission, and as such the molecular weight will drop and your solubility will increase. The type of functional groups you can get, like as I said, it goes from the hydroxyl to the carbonyl to the carboxyl, but where it happens is all dependent on the reaction conditions you prepare the starch in, or the oxidized starch in. So you can see you get different combinations of ring open with carboxyls, of carbonyls, aldehydes on the C6, or carboxyls on the C6, or you can get dialdehydes or diketones. So there's quite an array of different types of functionality that you get in starch, just with oxidation. It's one of the simpler, I suppose, reactions you can carry on. And if we're talking about changing the functionality of the chains, you're going to be looking at what mechanisms are required for it to absorb to your minerals. So if I'm talking about chalcopyrite versus carbon, I'm talking about, say, an acid-base type of interaction with the chalcopyrite and a hydrophobic interaction with the carbon. So these are the type of play we want to see with the functional groups with our starch. So as a first trial, I took some starch and I oxidized it with sodium hypochlorite, just at 3 levels, at 1%, 5% and 10%. And you can see on the left there that I've got a flotation response for just pure graphite and pure chalcopyrite. And you can see that those curves are quite close together, indicating there's not a very great selectivity between the two. Over on the right there, we've taken it at 120 grams per tonne, and you can see the blue is the 1%, the red is the 5%, and the dotted line is the 10%. And you can see that in between there, that red at 5% of the hypochlorite, we're getting quite a good difference between the depression of the carbon versus the compression of the chalcopyrite. So that sort of indicated, from an initial trial, that there's a possibility of being able to improve the selectivity. Concentrating on that one that was looking better for us, what I call Ox 5120, you can see on your left there, the chalcopyrite with the native wheat starch, NWS, and the graphite, our carbon proxy, are very close together. When we use the oxidized starch, chalcopyrite behaves quite similarly, but our graphite has depressed quite a bit more, so this is a promising type of situation. And just quickly, the types of absorption isotherms that we're able to establish with that. See up the top there, the chalcopyrite, and the bottom, the carbon, or graphite. The response for both is quite similar for the native wheat starch, and that sort of, I suppose, fits in with what's on the left there. But you're seeing quite a different absorption isotherm for the using the oxidized starch, where a greater weight of oxidized starch is absorbing to the graphite rather than the chalcopyrite. And we're assuming that's underlying why there is some sort of shift in selectivity. So we've got to work out why this is happening. And as I was saying before, with starch, you've got to unravel those granular structures to start with. And so if you don't do that completely, you're going to end up with supramolecular structures. So you end up with little shells or other, or just chunks of amylopectin. So we need that determines how soluble the material is. You've got to look at the molecular changes, and you've also got to look at the functional group changes. So you've got to work out which of these, or what combination of these structures are contributing to the better performance. A relatively simple way of working out the supramolecular structures, I suppose, is by looking at the kinematic viscosity. And what I do is just prepare a 2% solution, and I dilute that to various concentrations, and you just measure the time that it takes to run through a certain size capillary, and you end up with these curves here of kinematic viscosity versus concentration. Now, if you look at the black dotted lines, that's the results for the native wheat starch. You can see there's quite a big gap there. So what I've done, I've had a bulk sample, I've measured the kinematic viscosities of that, and then I centrifuge that sample and take out the top 2/3 of the centrifuge sample as the supernatant, and I repeat that process. And when there's that slope difference, that indicates that there's larger structures. It's not a completely homogeneous solution, and so that indicates those supramolecular structures that exist. You can see that for the hypochlorite oxidized samples, with the blue with the 1%, red the 5, and the green the 10, that those before and after centrifugation slopes are really quite close together. That indicates that you've got much more of a homogeneous solution. So one of the goals, I suppose, of trying to oxidize the starch was trying to improve that solubility, and so this is a way of seeing that that's occurred. For looking at our molecular weight changes, we've used our GPC, of course, and you can see there that on your left, that as we increase the oxidant, you go from the green of the native wheat starch. The 1% gets a slight little shift, is generally the amylose will produce that third species there at around 10 nanometers of the hydrodynamic radius. You can see there, but just to 5 and 10%, a lot of chain scission has occurred. The molecular weight of the material has dropped quite a lot. So in that, if you remember back to what I was showing you for those glucose units, this indicate ring opening and chain scission. So we've decreased the molecular weight of the material quite significantly there. If you look at the association of the functional groups, the carbonyls and carboxyls that are produced on the way to this, you can see there that the 1% you've got far, or slightly more I suppose, carbonyls than the carboxyls, and then as you go to the higher percentage of oxidant, that will invert and you'll get more carboxyls than the carbonyls. And we just so happen to see in this case with the 5% that our carbonyl carboxyl ratio of around 1% seems to be achieving something we want. Now, determining if it's the molecular weight or the functional group changes that are really contributing to our improved results is a bit of a challenge. You've got a very large molecules still with very subtle changes. So you can see there, these are only talking about less than 1-2%, less than 1% type of changes. So in the scheme of things, it's not very much, and it's hard to imagine that could be that effective. But with the mechanism of the hydrophobic interaction, all that, we're just trying to establish if that is exactly what is occurring. That the carbonyl is slightly more hydrophobic than the hydroxyls, and that could be just enough to get it to absorb to the carbon. Here's AFM images. On your left there is the just the native substrate. This is highly ordered pure graphite, so it might not represent the real situation that well. But anyway, you can see in the middle there you've got the native wheat starch, and you can see the right there that that's the Ox5 120. It's got a far more geometrical and ordered type of absorption of the polymer chains onto the surface there. Surprisingly though, when you have a look at say the roughness and the average height of between say B and C, the native wheat starch and the oxidized starch, you're getting more for the oxidized starch there. So again, that's pointing back to that chain scission and the ability for the glucose monomers to open and reorient, have greater steric freedom, and so they could actually be reaching out into the water phase, and once they're absorbed to the carbon surface, that could increase the ability for the depressant action. After doing that, we thought we'd try a few other starches. So of just native wheat starch, there's the three I just talked about. There's that pink one there is an oxidized commercially available starch from Manildra, and also a dextrin. Now the dextrin and the blue one there is an extruded starch, which is what we're trying to produce. So one thing we're trying to do is trying to find out what structures work, and then once we establish that, we want to use reactive extrusion to mass produce these things, moving from the solution chemistry that's usual to a continuous mass production via extrusion. So the fact that we're able to produce, in this case, the blue down on the right there is a 1% peroxide oxidized starch with a molecular weight that's pretty much in the range of the one that worked for the Ox5 120. So that looks promising. The dextrin works well as well, but again, it seems to depress the chalcopyrite quite significantly as well. So there's that selectivity problem. And again, because of that sort of change in selectivity, if we compared the dextrin with the oxidized starch, we're trying to work out the effect, the change in the functional groups, what's causing the difference between them. Like I was just saying, we're once we've discovered the structures that do work or look promising, we want to be able to produce those. This sort of calls back onto my polymer science and engineering background, is to produce those things with extrusion. Another thing is that if you think about ores and the way ores change through the life of mine, you won't necessarily need the same reagent or depressant all the time. Extrusion gives you the opportunity to flexibly and change your reaction conditions and be able to produce small runs or larger runs of a material. And so this will be the next stage of the work we're looking at. If we can do that, you've got the opportunity that we will be able to produce cold water soluble high or low molecular weight starches. If you can control the oxidation, be able to decouple that molecular weight and functional group change. And this getting, if we look further down the selectivity path and looking at different types of minerals, we're looking at, we could look at how things perform with the carboxymethyl groups or the esters or other types of functional groups. Like I say there, it offers a possibility of continuous flexible one-step production, but we only need to learn how to control it. All right, thank you. No, unfortunately not at the moment. We're hoping to get some ores to try, which we're hoping to get some ores to test the real situation. Yeah, because you're right, because the graphite is a quite of an ideal situation. So yeah, that would be what we were going to do. Yeah.
And how close is this to commercialization? Are there starches out there that are doing the job, or something totally?
There are a few like commercially available starches that we've tried, which do have variable performance, but it is finding those gaps in between the commercial grades that we're finding is what works. So, like I was saying, with getting that re-extrusion process going, where you don't have the infrastructure, say, of solution chemistry or that semi-continuous batch processes that is used to modify starches at the moment, we want to be able to do it in smaller, more nimble, flexible ways. So that's a work in progress at the moment, yes.
I have a question. Have you looked at other sulfide minerals other than chalcopyrite? Do you think it will make a difference?
I think it will. Yeah. We have a nickel talc story we want to look at. But at the moment, no, this is just the graphite and calco at the moment.
Thank you, Mr.
All right.
So our next presenter is Joseph Jankolovich. He's been a research scientist with Solvay Mining Solutions R&D, focusing on sulfide flotation reagents for 4 years. Prior to joining Solvay, he earned a PhD in inorganic chemistry from the University of Michigan, performing thesis research on the coordination chemistry of copper, zinc, and rare earth elements. And he did his postdoctoral research at the University of California, Berkeley, focusing on the surface modification and dispersion chemistry of inorganic oxides. And he's going to tell us more about carbon management.
Yeah. All right, thank you. So yeah, I'd like to talk today about carbon, and I think carbon goes by many different names, as I'll refer to it: graphitic carbon, total organic carbon, carbonaceous matter. You know, people can't really seem to agree on a name for it, but I think people recognize that it's a problem, and it causes many, many different problems. It's naturally hydrophobic material, so it floats naturally, tends to float alongside sulfide values and dilute concentrate grades. So you definitely see that in the metallurgy. It also causes a lot of frothing issues in the plants. It creates a very sticky and stable froth that's very persistent, and in some cases can actually require plants to actually operate at reduced airflows and increase froth depths. And so that alone can decrease value recovery. In addition, you actually get froth crowding effects that can decrease value recovery even more. Also, you tend to see very high reagent dosages when you're processing carbonaceous sulfide ores. It's because it's so hydrophobic, it absorbs reagents onto the surface. And you do see some downstream penalties, smelter penalties, preg robbing with carbonaceous gold ores is also really important to consider. And so with all these complex problems, both in the flotation standpoint, metallurgy standpoint, and downstream, you know, it's quite interesting to see that the actual solutions that are proposed for carbon management tend to be presented as something that's quite simple point solutions. You know, you could run a pre-flotation circuit with a frother only, generate a carbon concentrate. Your sulfide values are then in the pre-float tails, and they can proceed to the primary circuit where you can float them in a standard way. Or you can use a depressant in your primary circuit where you're adding an organic reagent to make the carbon hydrophilic so it does not float, alongside your sulfide collectors, generate sulfide value mineral concentrate, and then your carbon reports to the tails. And so these are sort of presented in a straightforward way, and they seem to have very simple flaws from a conventional view. The problem with pre-flotation is that it's unselective, so you lose values. The problem with depressants is that they're unselective, and so you lose values. And so, you know, what we recognize is actually the implementation of any of these strategies really requires understanding many, many different variables that impact flotation. You have to understand sort of how to make your reagent scheme work with either of these operations, make it work with the flow sheet and the ore type, and also the actual mineralogy of the carbon and the ore itself. And so what I'd like to do today is actually unpack a little bit what we call the holistic approach, how to understand all the variables that really matter to manage carbon and generate optimal flotation performance. Okay, and so what I did was I started out just by critically reviewing all the literature that's out there on carbon, distilled a few essential concepts from many different references, and then had a lot of discussions internally with experienced people at Solvay. What is the plant experience that we're seeing globally? And also critically analyze the flotation data we saw to really see how do these factors really matter. And what I'd like to do is sort of move beyond the idea of pre-flotation or depression as point solutions and move beyond the idea that it's an either or. Really both can be best. And it has to do a lot with mineralogy. So I'd like to talk about what the mineralogy factors are with carbon. And then also just go into some case studies and just conclude just by making an appeal for a holistic carbon management approach. Okay, and so just here's the most important concepts around carbon as a material and the mineralogy that are really important to understand how it impacts the flotation of sulfide ores. Okay, so the first is that carbon is a naturally porous material. Okay, micro, meso, macro porosity tends to be seen across a range of different carbon samples. And because of that, you tend to see very high reagent dosages. So just an example from Century Mine, pre-flotation concentrate had a surface area that was 50 times larger than what you would expect just based on its geometric particle size. So you tend to see very high reagent dosages, and more than that, this tends to be quite variable between carbon substrates or carbonaceous materials that you're processed in the plant. And so because of this, there's an immediate benefit to actually pre-floating off some of the carbon because you just remove some of this variability and your reagent costs become a little bit more manageable. Okay, so in addition to that, carbon tends to be very, very fine-grained. Primary particle size of carbon is typically less than 5 microns. Good example is Century Mine. Again, P80 of 90 microns in the pre-flotation circuit. 90% of the carbon in the pre-float concentrate was in the 5 micron fraction. And this is really seen consistently across a range of different sites. It's very rare to see any sort of coarse size carbon. And if you do, it's probably not liberated. Okay, and this has 2 real big impacts on flotation. The first is that carbon may actually float very, very slowly, not because of its surface chemistry, but because of its particle size. Fine particles frequently float slow. The second thing is that entrainment becomes a really, really prominent mechanism for carbon to actually report to a concentrate. So even if you have a perfectly effective depressant, you still may have a lot of trouble actually depressing carbon because of frothing issues, because of entrainment, and not because your depressant doesn't work. So this is, again, reasons why the entrainment factor, pre-flotation, can really be a good process to consider. Okay, and the last thing is mineral associations. And I think this is, to me, by far the most important and complex factor that really needs to be understood with carbon. The mineralogy tends to be intimately associated with values and with gangue minerals. And understanding this has a lot to do with the actual flotation selectivity that you see when you process a carbonaceous ore. It tends to lead to very atypical flotation behavior, where, say, pyrite will not be depressed with cyanide, and it's either because it's associated with carbon, or you can actually see carbon rimming, where you find basically a coating of carbon on the surface of either a value mineral or a gangue mineral. And you can really see this from some of the micrographs that I presented here that are out in the literature. On the top right, you see carbon is a dark-colored material, galena is light-colored, and sphalerite is gray in this carbonaceous polymetallic ore. That scale bar is 200 microns if you can't read it. So you can see association between carbon and your value minerals at a size that is much, much finer than you would actually liberate in any standard grind. And on the bottom, you see, again, a double refractory gold ore, or again, carbonaceous matter and pyrite, both of which actually carry gold values, are very intimately associated. Now, another factor with this that's actually coupled with the actual particle size of carbon being so fine is that carbon is very frequently locked, either in values or in gangue. And so because of this, recovery can actually be very limited in pre-flotation. Most pre-flotation circuits achieve maybe 25% carbon recovery for very good mineralogical reasons. And also, because of actual locking, complete depression is not necessarily achievable. It can be quite common to actually see carbon locked inside values. So even with a depressant in your rougher circuit, carbon can still report to the concentrate, and then it can actually be liberated in a regrind. So it can be important to actually add depressants at multiple stages throughout your circuit to manage that issue. Okay, and the thing that's probably least understood about carbon is actually its material composition and how it impacts flotation. So it's known that carbon can be very variable, and sort of the real correlation that's most useful is to think about it like coal, even though it is quite different. But as you have increasing sort of atomic carbon in the composition, it goes from lignitic, bituminous to anthracitic carbon. Becomes more hydrophobic, you have fewer and fewer oxygen groups, more and more aromaticity, and it tends to float better. You don't really see carbon floating if it doesn't at least sort of in the lignitic or bituminous type of material. And actually looking through the literature and looking at, people who have actually characterized the carbon in sulfide ores, you tend to see it falls into a fairly narrow range of bituminous or anthracitic carbon. And this means that it has aromatic domains in the molecular to nanoscale. Hydrophobicity is the dominant surface chemical feature. There are oxygen-containing functional groups, but there tends to be a small number of them, alcohols and ethers or phenols mostly. And so it's not really clear how much material composition really matters in sulfide mineral flotation. And I'd really caution that it has been used as a crutch to ignore very valid mineralogy factors in understanding carbon flotation. I think it needs further study. XRD and Raman are the techniques to use. But I think it's important to at least recognize that. Okay, so I'd like to just go into a few quick case studies, just really understand how mineralogy impacts carbon management. Okay, so just think about value losses in a carbon pre-flotation. I think there are multiple mechanisms that we can identify of how you could lose values. And so the first is true flotation, because carbon can actually be your values can be natural floatable, just coming out of the grind without adding collectors. So the approach there is to add sulfide depressants. There are many of them out there that we provide. We know how to apply them. However, you could also have sulfide value losses because of association. If you have this, you tend to see a linear correlation between carbon and your sulfide value across a range of different flotation operating procedures or reagent schemes. And this is actually fairly common to see. So another mechanism is entrainment, and this becomes very, very important to consider. If you're running a pre-flotation circuit, you will entrain values. It's inevitable. So one thing that I think is a must is to actually have pre-flotation cleaners. Red Dog was operating without a pre-flotation cleaner for a while, implemented one that was actually a Jameson cell. And when they turned it on, they really saw 2% substantial increases in zinc and lead recovery because of just minimizing entrainment that was returned to the primary circuits where they could be recovered in the appropriate concentrates. Now, in addition to the engineering approaches, there are also chemical approaches. I think the best actual method is to use chemical and engineering approaches in concert to really obtain the best metallurgy. But our commercial team developed a carbon collector to match the froth behavior of a carbonaceous polymetallic ore. And what they saw from the testing was actually a reduction in gold recovery that was entirely due to reduced entrainment because the froth properties were improved significantly. And what's quite interesting about this is that it is a carbon collector. People think that carbon collectors make surfaces more hydrophobic to increase carbon recovery or increase kinetics. But if you look at the kinetic data there, there's no change in the actual flotation kinetics. It's purely a froth phase phenomena. So actually understanding what the chemicals are doing can really have a substantial benefit to improving the actual metallurgy and optimization of the process. Okay, I'd also like to talk about depressants. So this is data from a depressant trial that our commercial team ran on a medium grade polymetallic ore. And so what you see in the metallurgy is actually what you would expect for an effective depressant. Carbon recovery goes down and lead concentrate grade goes up. And so that's what you see, and there's definitely a lot of benefits there. We saw some improvements in zinc circuit performance as well. But the true benefits in the plant really came from froth control. Carbon creates a very sticky, unstable froth, and it was forcing this plant to operate at significantly reduced airflows. It caused a lot, and there were significant operational stability issues, particularly with variation in the carbon head grade. And with the introduction of the depressant, now they could operate consistently, manage variation in carbon head grade. They could increase airflows, decrease their froth depths to maximize lead recovery in the lead circuit, so you had fewer lead losses to the zinc. And with that operational stability, now the plant's able to start optimizing other variables to actually maximize the overall circuit performance. Okay, and so what I'd like to conclude with is just to really think holistically about what a carbonaceous sulfide ore really looks like. And that because of the complexity of an ore like this, no point solution will really be effective. And you really need to think holistically about all the mechanisms involved of how you could lose values to, say, a pre-flotation concentrate, or all the reasons why carbon may not float, might not be recovered in a pre-float. And likewise with the depressant, there are many, many reasons why a depressant may lead to value minerals reporting to the tailings, or why carbon may actually report to the pre-flotation concentrate. And so overall, it's important to think about factors regarding carbon mineralogy and surface chemistry, its association, fine particle size, porosity, froth phase effects, mineralogical composition, along with the actual mineralogy of the ore you're trying to float, the processing strategy you select, and the other variables in terms of implementing these solutions in the plant and in the flow sheet to actually obtain your optimal metallurgical performance. Okay, and so I'd like to thank various members of the commercial team in North America and EMEA. I'm happy to take questions.
So if we think of sulfide ores, for example, do we find, what percentages of carbon might we find? Is it common to find this carbon? You know, could you speak about what we find out there in U.S. mining?
Yeah, and so it's definitely not typical. It tends to be by deposits. Tends to be more common in polymetallic ores. Actually, I'm hard pressed to think of any in the sort of the contingent 48 states that actually have carbon problems outside of the sort of the Carlin trend double refractory gold ores. But it's common in polymetallic ores. I think globally you see carbon in many different regions. Yeah, so it can be quite a big issue globally. Mm-hmm.
So it sounds like you have to try to depress it. Sometimes you have to try to flood it. Do you lean one way or another, or is your answer
Yeah, I think it depends on the nature of what's there, how much is present, and what its associations are. I think there are real benefits to pre-flotation as long as there aren't too many value losses. Or if there are value losses, if there's no alternative in terms of, say, a roasting strategy to actually separate it out the two. But yeah, I think what we see is that because of the reality of liberation of carbon downstream, say in regrind processes, a pre-flotation alone is rarely going to be sufficient, and frequently just because of carbon flotation kinetics, driving carbon recovery in a pre-float is going to lead to two substantial losses. Yeah.
Thank you.
All right, thank you.